next one in C. In C, we have y equals 4 over x. Well, as a little side note, you learn how to do these problems in college algebra, and you learn how to draw them based on their vertical asymptotes and their horizontal asymptotes. The vertical asymptote has to deal with when the denominator is equal to 0, which in this case, the denominator is equal to 0 when x is equal to 0. So you have a vertical asymptote at x equals 0, meaning your graph will get closer and closer but will never actually touch 0. Also, you do have what's called a horizontal asymptote. You learn about this in college algebra, and it's because the bottom is bigger, has a higher exponent on its x's, that what that means is it will have a horizontal asymptote at 0. Because what that means is the bottom's getting bigger and bigger and bigger faster. It means you're dividing by a bigger number. What happens when you divide by a bigger and a bigger and a bigger number is your number actually gets smaller and smaller and smaller and closer to 0. And that's all because the exponent on x is higher on the bottom, which means the bottom will get bigger faster, which means you're dividing by a bigger number, which means you're getting closer to actually 0. Continuing along in college algebra, what you learn is that the mock-up of this graph would look something like the following. You would have a horizontal asymptote designated by a horizontal line with little dashes, and then you'd have a vertical line or an asymptote at 0 as well along the x's. And then what you learn by plugging in values is that your graph is below on the left and above on the right, because it's just a regular x on the bottom. Now the question is, how do you actually find its inverse? We know that it will have one because notice that the graph does pass the horizontal line test. So if it passes the horizontal line test, it's 1-to-1 and it will have an inverse. So it has an inverse, we just need to find it. So how do we find the inverse? Remember that you find the inverse by swapping x's and y's. So what are we going to do? Well, our original function was y equals 4 over x, so swapping the x's and the y's would give us x equals 4 over y. But remember, just like all of our other previous examples, we have to solve for y. We're used to having a function solve for y. So how do I solve this guy for y? Well, I need to get y out of the denominator first. We can't solve for something if it's on the bottom. Well, it's on the denominator because you're dividing by it. So to get it out of the denominator, you need to do the reverse. You need to multiply by it. So we're going to multiply both sides by a y. That will get it out of the denominator and we'll move it to the other side. So now we'll have an x times y on the other side and just a 4 on the other. We're still getting the y by itself, so we'll divide both sides by x. So that gives me that y equals 4 over x. Well, this looks funny. Why does it look funny? Because notice, this is our inverse now. This y equals, and it looks just like the original function. But so that I don't get confused, I'm going to label it as f with a little -1 instead, so that I know that this is indeed my original, or is not my original function, it's my inverse. Remember, the little -1 means inverse. So this happens very rarely, but it does happen where the original function and the inverse are the same, and it's because what the original function does is it flips things over, meaning takes its reciprocal, and then what does the inverse do? It does the same thing. It divides it again, so it takes its reciprocal again, so that would flip it just right back to where it came from. It's pretty cool. Now, we're still not done. They wanted us to find the domain and the range of the original function. and of the inverse. So let's go ahead and take a look at that. Let's start with the domain of the original function, which means reading along the x-axis from left to right. And what you'll notice is the function does go forever in both directions, except for a big issue at the middle at 0 where our asymptote is. So we can go all the way up to our asymptote, so negative infinity to 0, union, and we can also go from 0 to infinity, but we can't include 0 because it's an asymptote. To make sure that we don't include 0, we're going to put parentheses at 0. That makes sure that we do what an asymptote says, is that we're going to get closer and closer and closer, but we will never actually touch it. Now let's look at its range, meaning looking at its y values here. If we look at its y values, again, reading along the y-axis from bottom to top, we notice we are pretty good from negative infinity to positive infinity, except for, again, at the middle here at 0. So its range is going to be the same idea. We can go from negative infinity all the way up to 0, and the union symbol means we can also go from 0 to infinity. But just like before, we've got an asymptote, this time a horizontal one at 0. So I have to leave out 0 and I'll use parentheses. Now, what we should notice is our inverse function is the same as the original, so it's going to have the same domain and range. But even if you weren't sure about this, remember, inverses have to do with swapping x's and y's. So the domain is going to become the range of the inverse, and the range is going to become the domain of the inverse. So what this means is our range for our inverse is going to be our domain from the original function, because we're just swapping x's and y's. So it'll still be negative infinity to 0, union 0 to infinity. And the range of the the domain of the inverse will be the range from the original function, because again, we're just swapping x's and y's. But we should have known this anyways, because they're the same function, that they should have the same domain and range. Either trick works each and every time. In D, we notice we have fractions again.